Okay, Matt Roscoe here at the University of Montana with a lecture on Wilson's theorem from our chapter 5-3 of our course in number theory. So we already talked briefly about this, just to sort of recap. In 1770, there was this English mathematician, Edward Waring, who included in one of his publications an interesting property of primes that his student John Wilson had discovered. So the property is aptly named after his student, as Wilson's theorem. No proof of the property was provided, but the property did catch the eye of Lagrange, who in 1771, a year later, provided a proof. This was the theorem in question. It's that if p is prime, then p minus 1 factorial is congruent to negative 1 mod p. Of course, that's the same thing as saying p minus 1 factorial is congruent to p minus 1 itself. Let's take a quick look at an Excel file that will let us, I guess, verify that this is indeed the case. So if I go to our Moodle page, sorry, I should have had this already up. So here we are, number theory. And if you go to our section on Fermat's theorem, here you'll see that there's a factorial congruence Excel file. It looks like this. And I guess the thing to take a look at would be if we choose sort of a smaller module 5, that when we take x as 4 and we compute the residue of x factorial, so 4 times 3 times 2 times 1 mod 5, it's congruent to 4. So in other words, p factorial, p minus 1 factorial, sorry, is congruent to p minus 1. Of course, 4 is congruent to negative 1, so that also, I guess, the statement of the theorem says it's congruent to negative 1. If we look at other cases, 3, of course, should work. So 2 factorial is congruent to 2. Anytime this is prime, it should work. 7 should work, so 6 factorial is congruent to 6. 11 should work, so 10 factorial is congruent to 10. 13 should work, so that means 12 factorial is congruent to 12. But quickly, I think we run out of computational space. Well, no, it still works for, no, it doesn't quite work for 16. We get to 1 before the answer here, but at 16 factorial, we're too big to compute a modulo. One interesting question you might have is, well, what happens if it's not, I guess, if the setting is not a prime setting? And at first glance, you can see that things fall apart pretty rapidly. It turns out that once you're past 3, everyth's congruent to 0 mod 6. And the reason that is because you have a 3 and a 2 now in the factorial computation. And so you see things kind of fall apart when we're not in a prime modular setting. Same thing should happen. Let's see if I go to 8. Once we're past 3, in other words, when we get to 4, then we have, I guess, 2 to the third is included in the prime, I guess, the factorial computation. There's a 2 and a 4, so everything's a multiple of 8 past 4 factorial. Same thing's going to happen with 9, I think. Once we're past 6, there's 2 factors of 3 in there, so you'll end up being a multiple of 9. So you can see this is a special case that works really only when we are in a modular setting that's prime. And that's the only setting really when we actually get a residue for everything up to, I guess, p minus 1 factorial. And what this allows us to do is compute, I guess Wilson's theorem allows us to compute that last one before everything's congruent to 0, mod p. Okay, well, let's keep going then. We should probably prove this. Let's go ahead and review the proof that Lagrange submitted for this. So here we go. See if I can get this a little bit bigger. So our hypothesis is for prime p, p minus 1 factorial congruent to negative 1 mod p. So that's our hypothesis. Let's go ahead and construct a proof. we're going to proceed directly, so no induction or anything like that. First, observing that when p is equal to 2, then 2 minus 1 factorial, that's just equal to 1 factorial, which is just a 1, which is congruent to negative 1 mod 2. When p is equal to 3, then what? 3 minus 1 factorial is going to be congruent to 2 factorial. 2 times 1 is just 2, so that's congruent to 2. And 2 is congruent to negative 1 mod 3. So we're going to just sort of knock the even and first one off, and now we're going to take p to be strictly greater than 3. In other words, I showed that it worked for 2 and for 3, so in other words, this thing is proven for first two cases. But now we're going to say p is strictly greater than 3. Then we're going to go ahead and let a be any of the integers in the set. And the set I'm going to put down as 1, 2, 3, let's call it 4, dot, dot, dot. Maybe I shouldn't do 4 just in case we have 5. Let's see, so 3, dot, 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 all the way up to p minus 1 in the setting. So again, now p is something greater than 3, so that means that, you know, it could be 5, so this would be, I guess, up to 4. It could be 7, so this p minus 1 would be 6, but this is an expandable set that goes up to p minus 1. So we're going to talk about that, and we're going to say a is one of the, I guess, the integers in this set. And what we're going to look at is the linear congruence. We're going to look at the linear congruence a times some x congruent to 1 mod p. I'm going to put a little star by this because I'm going to be referencing it. So the first thing to notice is we know that these things have a solution when the GCD of a and p divides 1 in this case, right? But since a is chosen from this setup here and everything's, you know, less than or equal to p minus 1, and p is prime, then these a and p are going to have to be relatively prime to one another. So what we're going to notice is that the GCD of a and p is equal to 1, and so a unique solution exists. Modulo p. So I guess what I'll say is hence there is some, let's call it a prime, that's going to be congruent to x mod p, such that I guess it'd be a times a prime will be congruent to 1 mod p. So in other words, this is kind of interesting to think about, right? That means that a, if it's chosen from this list, has some other a prime, and since these are all the residues less 0, and it couldn't be 0 because we're multiplying together to make 1, that means there's some partner pair in here that I could multiply one of these numbers together with another one of these numbers to get 1. In other words, so we can kind of think of the numbers in this list as pairing up as almost like multiplicative inverses, right? multiplicative inverses are things like 2 and 1/2 or 5 and 1/5, two numbers that when paired together multiply to make 1. But in this case, because we're in a modular setting, the two numbers are whole numbers and they can be multiplied together to make produce 1 so long as the setting is prime. Now, one question we might ask is it possible for a number to be paired with itself to make 1? And of course, that's true with the case of 1, but it also turns out to be true with the case of p minus 1. Those two, when paired together, produce the 1. But it turns out they're the only ones, so we want to make sure that that's the case here. Next, we show that A is congruent or equal to, now let's say congruent to A prime mod P if and only if A is equal to 1 or congruent to 1 mod P, or A is congruent to P minus 1 mod P. So you can kind of see how this works in the forward sense. So this is kind of like a mini proof inside of the proof. For if A congruent to 1, then 1x, I'm going back to this thing, A is 1, so 1x is congruent to 1 mod P implies that x is congruent to 1 mod P. So in other words, the only way I can get to 1 with 1 is multiplying by 1. And if A is congruent to P minus 1, then what do we get? We get P minus 1 times x congruent to 1 mod P. Let's see, so one way we could do this is we could kind of think of this as, we could just multiply these things together. So it would be xp minus x congruent to 1 mod P. What am I doing? And any multiple of p, of course, is congruent to 0. So what do we get? We get negative x congruent to 1 mod P. And if we multiply both sides by negative 1, we get x congruent to negative 1 mod P, which is just x congruent to P minus 1 mod P. I hope you can see that. Yep, you can see it. So what does that mean? That means that A prime, not A sub 1, A prime in this case is congruent to P minus 1. So certainly works in the forward direction. If A is 1, then x is 1, and here A prime would be 1. If A is P minus 1, then x is P minus 1, so A prime would be P minus 1. But we also have to have the converse, right? We want to show that that if the two are equal, then they're either if A and A prime are equal, then they're equal to either 1 or P minus 1. And let's just make sure that's true. So I'll say for the converse, let A be congruent to A prime mod P. And then what do we get? Then let's see. Then if we sort of compute A times A prime, we can say that that's the same thing, since these are equal, as A squared. And we're saying that thing is congruent to 1 mod P. So we have two numbers equal, and if the two numbers are two numbers chosen from our list, and if we multiply the two numbers together and they're congruent mod P, then when we multiply them together, it's the same thing as squaring one of them. and what we want that to happen, what we want in that case to happen is for that to be equal to 1, and what we want to show is that the only way that can happen is if that number is 1 or that number is p minus 1. In other words, there are no other, I guess, numbers in this list between 2 and p minus 2 that square to make 1. So let's find out and see if that's true. So if we start with this thing and subtract 1 from both sides, we get what? Let's see. So if I subtract 1, I get a squared minus 1 congruent to 0 mod p. And of course, this is the same thing as a plus 1 times a minus 1 congruent to 0 mod p, which implies that, so the only way we can multiply together to make a 0 is if one of these guys was 0. So this is the zero product property, right? It's the only way we get a 0 out in modular arithmetic or in any quadratic situation, right? When we can write things as a product congruent to 0. So either a plus 1 is congruent to 0 mod p, or a minus 1 is congruent, I don't need parentheses there, to 0 mod p, which implies here that a is congruent to negative 1 mod p, and if a is congruent to negative 1, a is congruent to p minus 1, and here we get a congruent to 1 mod p. So what we've just shown is if any number times itself is congruent to 1 mod p, then that number has to be one of these two numbers, 1 or p minus 1. So in a sense, in this list, these two on the end of the list are special because they're the ones that pair with themselves, I guess, to solve this congruence, congruent to 1. So let's continue now. Omitting choices of 1 and p minus 1 from our list, we are left with, well, so we don't have a 1, so we start with a 2, 3, and we go all the way up. Instead of to p minus 1, we go up to p minus 2. And since we know that this thing has to have a solution by linear congruence theory, and that the only time this has a solution where the x is itself is 1 and p, then everything in this list has to pair up with some other element in this list to solve, right? We're left with this, and each member of the list pairs with some other member, which is not itself, right? Such that, what, first of all, a is not congruent to or not equal to a prime mod p, and a times a prime is congruent to 1 mod p. So in other words, in this list there are these dancing partners such that when I multiply one by the other, I'm going to get congruent to 1, and they pair up exactly one with another. So how many of these are there? Now these, so we have p minus, I guess, 2 here and 1 there, right? So I guess it's p minus 3. And since they're paired, we can kind of cut it in half. So there are these p minus 3 over 2 pairings. Can then be multiplied together to get what? Well, we don't really know who pairs with what, but we do know that 2 times 3 times 4 times all the way up to p minus 2. Somewhere in this list there's 2 of them that dance together to make 1. Somewhere in this list there's 2 that when multiplied together make 1. And they'll all pair together to basically multiply together to make this p minus 3 over 2 pairings, all of which are 1. So these guys are all congruent to 1 mod p. So which is equal to, and I don't know if you notice this is dangerously close over here to a factorial. We're missing the 1, which we can just throw in, and we're missing the p minus 1 here, right, which is part of Wilson's theorem. So which is equal to what? It's equal to 1 times 2, or I guess not equal, it's which implies, I should say, so 1 times 2 times 3 times 4 times all the way up to p minus 2. And let's go ahead and multiply both sides by p minus 1. Make this congruent then to p minus 1 mod p. We're almost there. This whole thing now on the left-hand side is just the p minus 1 factorial. And this thing on the right-hand side is p minus 1, which is also congruent to negative 1 mod p. And so ends the proof. So this is a really interesting proof in my opinion, because it's getting dangerously close to some things in group theory that you're going to learn about in abstract algebra. But the idea is that this guy, again, has solution because the GCD of A and P is 1. So in other words, there is some x in the set of residues that can be paired with every A in the set of residues such that the product is equal to 1. And the only time they pair with each other are when they are 1 and P minus 1. And so what we do is we disallow 1 and P minus 1 from the list, and we say that all the rest of them have to pair with a partner. Now pairing with a partner is nice because each one of those partners is congruent to 1. So when we multiply the list out, these partner pairs, although they're not next to each other, they're definitely in there, the partner pairs will all be equal to 1. So that's where we get this equal to 1. We throw in an extra 1 and a p minus 1 on the end, which puts a p minus 1 on the other side of the congruence, which is equal, congruent, of course, to negative 1, and that ends the proof. And that's the proof that Lagrange showed to show that Wilson's theorem was indeed true. Now, sometimes it helps to do this with an example, and your book does this, and I think I'd like to do it too today just to show you that what's going on here. So for a concrete example, let's take 11, okay? So Wilson says that, let's see, 11 minus 1 factorial is going to be congruent to negative 1 mod 11. So let's just show how the proof sort of works here using numbers. So the way the proof works is you look at the integers, look at 2, 3, 4, all the way up to, remember p minus 1 is thrown out and it's p minus 2, so it would be all the way up to 9. And these can be paired, in such a way that the product is 1. And let's just do it. Let's just find these pairs. So it turns out that 2 can be paired with 6. 2 times 6 is 12, and 12 is congruent to 1 mod 11, right? And it turns out 3 can be paired with 4. That's 12, congruent to 1 mod 11. Let's see, 5, we want it 1 away from a multiple of 11, and 44 is a nice multiple of 11, 1 away, so this one pairs with 9 mod 11. And let's see, 6 can be paired with 2, congruent to 1 mod 11. And I guess I didn't really need to do that because 6 and 2 are already there. 1, 2, 3, 4. 1, 2, 3, 4, 5. Who are we missing? 7 and 8. And so what's kind of interesting here is the last one, 7 and 8, pair with each other, right? Just by elimination. 7 and 8 is 56, 1 away from 55. 1 mod 11. And now really what Wilson's does here is it just says, well, stack and multiply all of this, right? So on the left-hand side, what do we get? We get 2 times 3 times all the way up to 9, right? On the right-hand side, we get that congruent to 1, mod 11. Okay, so let's just go ahead and finish this up. That means that 1 times 2 times 3 all the way up to 9 times 10 will be congruent to 10, mod 11. So I just multiplied both sides by a 10, added the 1 in because the 1 doesn't change anything. So what we get on the left-hand side is 10 factorial. On the right-hand side, we get congruent to 10, but of course 10 is the same thing as negative 1, mod 11. And that's exactly what we have up here, right? 10 minus 1 factorial, or 11 minus 1 factorial, or 10 factorial is congruent to 1. This is Wilson's. And so you can kind of see what happens is that these numbers, just so long as they're not congruent to either 1 or p minus 1, in the list, they all pair together to create ones. And so that's the way that's the sort of the interesting fact, or I guess the piece that we're really, I guess, leaning on when we prove Wilson's theorem. Something happened there. Go ahead and close that out. So the converse of Wilson's theorem is also true. It turns out that if n minus 1 factorial is congruent to 1 mod n, then n must be prime. And at first it seems like, wow, so this could be a way that we could find primes. But if you think about it, it actually becomes really cumbersome in a hurry because we're computing factorials. And so it's really a pretty small, I guess, value to us in terms of any usefulness. There is a proof to the converse of Wilson's theorem in your book, and I won't go into it, but you can take a look at it in your book if you'd like. So let's do an example here. Let's show that 18 factorial is congruent to negative 1 mod 437. Let's see if I can bring up my overhead again here. I don't want that thing. I guess I want this thing. All right. 18 factorial congruent to negative 1 mod 437. So I guess the first thing we should ask is 437 prime? And so I would hit the square root of 437. I mean, I'm roughly in the 20s. So I would check all the primes up to 20, and it turns out that 437 divided by 19 is equal to 23. So no, not prime. So we're stuck with sort of working with these two primes and trying to sort of together use them to get some, I guess, combine results in these two prime settings to create a result, I guess, in this composite setting. So let's see what Wilson says about these two settings. So the first thing I guess you would say in mod 19, Wilson would say that 18 factorial is congruent to negative 1 mod 19. And let's check out 23. Let's see. So in the 23 setting, it would say that 22 factorial is congruent to negative 1 mod 23. So these are both by Wilson. And what does that mean? I guess that means that 19 divides 18 factorial minus 1. And it also shows us that that 23, I guess, well, this is the hard part. So we've got 19 dividing 18 factorial minus 1, and what we really need is we really need to have 23 dividing the exact same thing. That if both 19 and 23 divided this, then we could conclude that the product of 19 times 23 would divide it, because these two guys are relatively prime. So let's take this guy and work on it a little bit and see what we can get. Now really what we want is we want an 18 factorial. So what I'm going to do is I'm going to bust out 22 times 21 times 20 times 19 times 18, and we know that that guy is congruent to negative 1 mod 23, or sorry, times 18 factorial. And now the big question is this stuff has to reduce to 1. I mean, the reason it has to reduce to 1 is because we know that if we're supposed to prove this, then certainly 23 must divide the difference between 18 factorial and negative 1. Oh, and actually it's 18 factorial plus 1 up here. I'm sorry. I just noticed it's negative 1. Okay, so let's just sort of get a sense of what's going on here. It turns out that if I reduce some things, 22 times 21, it turns out that that guy is congruent to 2. So I'm going to reduce some things, and then if I take these two, multiply them together, divide by 23, then the residue they leave is 12. So we have 2 times 12 times 18 factorial congruent to negative 1 mod 23. So just sort of a modified Wilson's result, right? And then 2 times 12 is 24, and 24 times 18 factorial congruent to negative 1 mod 23. And 24, of course, is congruent to 1, so this means that 18 factorial is congruent to negative 1 mod 23. So what does that give us? That gives us that 23 then divides 18 factorial plus 1. So I have kind of the two pieces I need, this one up here and this one up here. So I'll just call this 1 and this one 2. So by 1 and 2 and GCD of 23 and 19 equal to 1, we get that the product 19, sorry, I'm running out of lead. So 19 times 23 must also divide 18 factorial plus 1, or just that 18 factorial must be congruent to negative 1 mod 19 times 23, which is 437. I hope that gives you a good sense of roughly how Wilson's could be used to prove a statement like that. It turns out that there's some nice extensions of Wilson's theorem to quadratic congruences, and this is sort of the first time we're going to delve into this subject, but it's going to feature largely in the end of the course. But we know now how to solve linear congruences. I guess the next place to go is to quadratic congruences. So these are things where we have a quadratic equation on the left-hand side, and we're trying to solve congruences that involve them. So it turns out that one special case that can be understood using Wilson's is with the quadratic congruence x squared plus 1. Whenever we're in a modular setting that's prime, then it turns out if p is an odd prime, it has a solution if and only if p is congruent to 1 mod 4. So in other words, it's p is 1 greater than a multiple of 4. So for example, this would have a solution when p is equal to 5, but it wouldn't have a solution if p is equal to 7. Let's take a look at some, I guess, some places we can get some intuition here, and take a look at this 5-3 quadratic congruence explorer. So this is the residue for x squared plus 1, and we can start it anywhere we want, and calculate it for any modulo we want. So if we take a look at 5, we can see that x squared plus 1 does indeed have two solutions, kind of like we'd expect with a quadratic. The two solutions are 2 and 3 mod 5. So in other words, x squared plus 1 congruent to 0 has two solutions when the modular setting is 5. But according to this theorem that we just presented, if it's 7, it shouldn't have a solution, and indeed it doesn't. Do you see that? So when x squared plus 1, when its residue is calculated, and of course the only residues you need to really look at are the first 6. Yeah, am I right there? I guess. Yes, I guess the first 7, because 0's not in there. I guess if I started this at 0, if I went up to 6, so that's going to be the periodicity of the table, right? And turns out when we're in mod 7, this thing's only congruent to 1 if x is 0. So no solution, I guess, in the integers other than 0. That's weird. So why would 0 squared plus 1 congruent? Oh, I'm sorry. We're looking for a 0. We're actually looking for it to be congruent to 0, not to 1. So no zeros show up anywhere in here, whereas in 5, zeros do show up. So in other words, the quadratic x squared plus 1 is congruent to 0 twice, mod 5, never congruent to 0, mod 7. Now let me ask you this. Will there be a solution for modulo 11? And think about it to yourself. What does this theorem say again? So this theorem says that there's a solution if and only if p is congruent to 1 mod 4. So let's take a look at this again. Would 11 work? So 11 isn't congruent to 3 mod 4, so it shouldn't work. And indeed, there are no zeros in there. Let's take a look at 13. 13 should work because 13 is congruent to 1 mod 4. It's 1 more than 12. And again, there are two solutions in there. You can see for 13, 5 and 8 work. 5 squared plus 1 is 25 plus 1, 26, right? 8 squared is 64. 64 plus 1 is 65, and 65 is 13 times 5. So kind of interesting. It looks like solutions for this particular quadratic are restricted to primes just so long as the prime is congruent to 1 mod 4. Let's take a look at one more. How about 17? Do you think 17 should work? 17 is 1 greater than a multiple of 4, so there should be two solutions here. And there they are. It looks like both 4 and 13 are the solutions. But 19 should not work because 19 is congruent to 3 mod 4. And again, there you see it for 19. No solutions where the residue is equal to congruent to 0. So I hope that gives you a sense of what the theorem is stating. There is a nice, I guess, proof to this in your book. I thought it'd be kind of nice just to sort of get a walkthrough of the proof. And I have this sort of handout to take a look at. And put the proof on a page, and we can make some notes on it. So let's just kind of see if we can get a handle on how it's being proven. Let A be any solution to x squared plus 1 congruent to 0 mod p. So that means that if A is a solution, then A squared is going to be congruent to -1, just adding -1 to both sides. And then because P doesn't divide A we can kind of think of as a residue, right? And so that, you know, P can't divide A. We can go ahead and apply Fermat's theorem. So it turns out this is where Fermat's theorem comes into play. And here's Fermat's theorem. This part right here, right, is Fermat's. It says that A raised to the P minus 1 is congruent to 1 mod P. But then they do a little work on it. They want to talk about A squared, and the reason they want to use A squared is because we have this piece right here about A squared that we can use. So instead of writing as A raised to the P minus 1, they raise A to the second power and multiply it by P minus 1 divided by 2. So I hope you can see that's just a tricky algebraic substitution. And then they go ahead and they substitute in -1 for A squared because we know A squared congruent to -1, and we get this expression right here. So then the idea is, well, let's just take a look to see what if P is some 4k plus 3. In other words, if it's congruent to 3 mod 4, it'll be written this way. And it can't, he says it does not arise. I mean, really what he wants to say is that it's impossible. For if it did, what would happen if we substitute 4k plus 3 in for this middle expression, or sorry, for p minus 1, then what you get is you get 4k plus 3 minus 1, which is really 4k plus 2, and 4k plus 2 divided by 2 is 2k plus 1. And what that would give us would be sort of a negative 1 raised to an odd power. And a negative 1 raised to an odd power, of course, is just negative 1. And that would give rise to negative 1 being congruent to positive 1 mod p, which is, of course, impossible. So we're done at that point. They have to be of this form. And the reason they can't be 4k plus 2, of course, is because any prime can't be written as 4k plus 2, and any prime can't be written as 4k. So the only options are 4k plus 3 and 4k plus 1 for primes, if they're odd primes, so other than 2. So for the opposite direction, the way that he gets it is he says, take this product. He says, just take p minus 1 factorial. And that's equal to sort of this set of, I guess, 1 times 2 times, and then you get to the sort of halfway point, p minus 1 over 2, p plus 1 over 2, all the way up to p minus 1. And he's saying that we have these congruences. So in other words, p minus 1 is the same thing as negative 1, right? P minus 2 is the same thing as negative 2. P minus 3 is the same thing as negative 3, all the way up to the break point in the middle where p plus 1 over 2 is congruent to p minus 1 over 2. And so what's kind of neat is that we can kind of think of rearranging these factors in p minus 1 factorial to be 1 times negative 1. In other words, you know, it's going to be this one times this one, right? Which is negative 1. So this guy is your negative 1, this guy is your negative 2, and so on. So if we just put those guys together, we get something that looks like this: negative 1 times negative 2, sorry, 1 times negative 1, 2 times negative 2, all the way up until we get to the break point where it's the middle term times the negative version of the middle term, which means that each one of these guys is squared, right? And it's a product, so we can put the square outside and say all of these are being squared, except for we have some negatives to deal with. And it turns out the right number of negatives is p minus 1 over 2, because there are p minus 1 terms here, and half of them are negative. So because there are p minus 1 over 2 minus signs involved, it's at this point that Wilson's theorem can be brought to bear. For we know that p minus 1 factorial, this guy over here, is congruent to negative 1. So that means that this guy is congruent, I guess, you know, we're just replacing this with a negative 1, and we're replacing this with this, and we're saying that negative 1 has to be congruent to all of this complicated expression, right? He's rewriting this sequence of products as a factorial. And then if we assume that p is of the form 4k plus 1, then this guy is positive 1, right? Which then leaves us with this congruence, right? And the congruence, you know, basically is the conclusion that the integer p minus 1 divided by 2 quantity factorial it's a solution, right? It's something that satisfies the congruence. So in other words, when we choose a prime of this form for our setting, then there is a solution such that that solution squared is congruent to negative 1, or another way of saying it is that solution squared plus 1 is congruent to 0. So I hope that gives you a little bit of insight into how that theorem arises. It's kind of a nice proof, because we see that it uses both Fermat's for the forward direction and it uses Wilson's for the reverse direction to prove its case. So let's take a look at sort of how this so the idea would be two quadratic congruences below, which one will have a solution, and then find it. Let's go ahead and sort of talk about this. Of course, our quadratic congruence explorer would find these for us, but let's go ahead and do this really quick. So I should have written them down before I moved, but x squared plus 1 congruent to 0 mod 19, and x squared plus 1 congruent to 0 mod 17. So let's see, 19 is equal to 4 times, what's the closest multiple of 4? 4 times 4 is 16 plus 3, and 17 is equal to 4 times 4 plus 1. So this guy is of form 4k plus 3, so no solution. This guy is of form 4k plus 1, so the solution exists. So we're going to work on this one, x squared plus 1 congruent to 0 mod 17. And what we're really looking for are two numbers in the lists, I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I guess 13, 14, 15, 16. We're looking for a number when squared is congruent to negative 1, mod 17. And it turns out that 4 works out really good. Well, 1 squared, you can see plus 1 will not work. That's congruent to 2. 2 squared plus 1 is congruent to 5, so that doesn't work. 3 squared plus 1, well, that's 9. 10, that's congruent to 10, doesn't work. But it turns out 4 squared does work, right? Because 4 squared is plus 1 is going to be, what, 16 plus 1, which is congruent to 17, which is congruent to 0, mod 17. So we found one of the solutions in 4. And it turns out that you have to search quite a ways. I'm not going to do it on camera, but it turns out 5 doesn't work, 6 doesn't work, 7, 8, 9, 10, 11, 12, but 13 actually does work. 13 squared plus 1, that's 169 plus 1, which is going to be equal to 170, which is congruent to 0 mod 17. And so these are the two solutions that you get. And just like in quadratic settings in solving quadratic equations with the quadratic formula, the number of solutions that you get is of course 2 for a quadratic, I guess, congruence equation. So I hope that gives you some insight into how Wilson's theorem can be extended. It turns out that it's Wilson's and Fermat's are pretty important in proving this, I guess, a small result about quadratic congruences. We'll see a lot more about quadratic congruences as we proceed in the course. That's really all I have to share from that chapter. I'm going to go ahead and stop the lecture now, and I'll see you when I get back.